Alright everyone, welcome back. Today we're going to introduce the topic of implicit differentiation of functions that are expressed implicitly and explicitly. Now up to this point in the class, most of the functions that we have seen have been expressed in what's called explicit form. So for example, the explicit form of this equation, y equals 3x squared minus 5, here we know explicitly that this is a function of x, that y is written as a function of x. So here, y is written explicitly as a function of x. The value of y depends clearly on x. Okay? Now, another example of this will be the function y equals 1 over x. This is now, we can see that this is expressed explicitly in this form. However, we could do the following. We could multiply y times x and 1 times 1, cross multiply. And if we were to do that, then we get x times y equals 1. Now this function right here is implicit. It's defined implicitly because we could solve for x, and now we have that x equals 1 over y. So it's not as clear. So when we take another derivative of something like this, if you begin with an implicit function, so somebody gives you x times y equals 1, then one way of, taking the derivative of this is to first write it explicitly, which we already have up there. We solve for y, so we get y equals 1 over x. But we know that by the rules of exponents, this is the same thing as x to the minus 1 power. We just bring that to the top. And then when we take the derivative of this, if we're to take the derivative, we know that dy dx, derivative of y with respect to x, is equal to minus x to the minus 2. Because remember, we bring down the 1 to the front, the minus 1, and then we take away 1. Minus 1 is minus 2, and then minus 1 times x is minus x. So this is just simply negative 1 over x squared. Okay, so note, if you are given a function implicitly, then you can try to write the function explicitly in terms of x and y and take the derivative. However, this is not always often possible. So it's not always possible. For example, what if you're given this? Let's say you're given x squared minus 2y cubed plus 4y equals 2. Well, how would you find the derivative of this? So if somebody told you to find the derivative of y with respect to x of this, it will not be as easy. I mean, you could try to move the x term to the right side, let's say, right? So your instincts may tell you to do this, but then, solving here for y is actually very difficult. Separating this is not as easy as you may be used to, and it will take a lot of work. So to find the derivative of y with respect to x, we use something called implicit differentiation. So to find dy dx, we will use implicit differentiation. Okay? All right, so first of all, to find the derivative of a function implicitly, you should first realize that the differentiation is taking place with respect to x. It's taking place with respect to x. Now, this is something that when I first introduced the derivative, I told you that when we write dy dx, this means the derivative of y with respect to x. So we're taking the derivative with respect to the x variable, not the y variable. Now, when we take the derivative of a function that's defined implicitly, then we differentiate as we normally do. However, we have to apply the chain rule because we will be kind of ignoring the fact that the y's are there. So we have to use the chain rule. So for example, let me just illustrate this with an example. If you take the derivative with respect to x of x cubed, let's just start with this. Notice that here, I'm taking the derivative with respect to x, and I'm taking the derivative of something that has an x term in it. That's x cubed. If this is the case, notice that these variables agree. If this is the case, we will use a simple power rule. We use the power rule. And remember the power rule, if you have something of the form x to the n, if you're taking the derivative with respect to x of something of the form x to the n, then that's n x to the n minus 1 power. So this is going to be 3x to the power 2, because 3 minus 1 is 2. So the derivative of x cubed is 3x squared. And we're done. We don't have to do anything else. But what if we have, let's call this A. What if we have the following scenario? What if we now are taking the derivative with respect to x of y cubed? So almost the same idea as before. Notice here that these variables are not the same. So the variables are not equal. So in this particular case, we will use the chain rule. So here, we use the chain rule. And how do we use the chain rule? Well, your u, you're going to say that u is equal to y cubed. And that means when we take the chain rule, that we're going to have the derivative of u times u prime. So we're going to have the derivative of y, we're going to take it normally as we did with the x up here. So instead of writing y cubed, I'm going to write the derivative of it, which is 3y squared. But now I'm going to multiply by u prime. And here, u prime is not going to be, we're not going to write, 3y squared again. That's clearly the derivative of u. What we're going to do is we're going to write dy dx. So because the variables were not equal, we will multiply by dy dx. Whenever we take the derivative of y's, we will always write dy dx. next to the derivative that we just took. So let me illustrate this once more. So let's say you're taking the derivative, again, with respect to x, of x plus 3y. If you're taking this derivative, then you'll take the derivative of x as usual, that's just 1. And now this term has a y on it. So you'll take the derivative as usual of that, so that's plus 3. And then what you're going to do is you're going to multiply by dy dx, because you took the derivative of y with respect to x. So wherever you see a y term, you're always going to add dy dx when you take the derivative with respect to y. Let's do one more. And we're going to do a lot of examples of this anyway, this lesson. Let's do this one more. So d dx of x times y squared. Here, notice that we're multiplying two variables together, or two functions together. You could think about the x as just being the line y equals x, and then y squared, you could think of that as being a parabola. You could think of that as being a parabola. Obviously, there's a difference in the axis, but you could think of that as being a parabola. But anyway, it's two different functions that you're multiplying together, so we have to use the product rule, because you're multiplying two different things. So remember, the product rule said that you've had f times g, that is equal to the first times the derivative of the second, plus the second times the derivative of the first. So if we were to do this now, and I follow the rule, I'm doing the first, which is just x, times the derivative of the second. The derivative of y squared is 2y, but because I took the derivative of a y value, I will write dy dx as well. So again, every time we take the derivative of something involving y, we will add dy dx. Now by the formula, let's continue. I have g times f prime, so plus the second, which is y squared, times the derivative of the first, which is just 1. Notice here that I'm not writing dy dx because I never took the derivative of this term for this second piece. We could simplify this a little bit more. This is 2xy dy dx plus y squared. And this is just some scrap work. Okay? So most of these problems will boil down to this. Whenever you see a term involving y's and you take the derivative, and you take the derivative implicitly, you'll add dy dx. So let me give you some guidelines. So guidelines for implicit differentiation. So number 1, you will differentiate both sides of the equation with respect to x. Number 2, you will collect all terms involving dy dx, meaning anything that's being multiplied to dy dx, and you'll move them to the left side of the equation, or the equal signs. On the left side of the equation. And then you'll move all other terms to the right side. So if there's something that doesn't involve the dy dx, you move it to the right side. We'll do more examples of this. We'll illustrate this. The third step is to factor, so as to factor dy dx out of the left side of the equation. And number 4 is to solve for dy dx. typically by dividing both sides of the equation. By the left-hand factor that does not involve dy dx. Okay, what do I mean by this? So let's see this again in action. So let's say somebody in the training tells you to find dy dx for the following. For y cubed plus y squared minus 5 minus x squared equals -4. All right, so what is the first step? So if we move up here, the first step is to take the derivative of both sides with respect to x. So I'll take the derivative, actually right away I'll take the derivative. So again, wherever I see a term involving a y, I'll take the derivative normally, but then I'll multiply it by dy dx. So the derivative of y cubed we saw before is 3y squared. And now because of the chain rule, I'm going to multiply this by dy dx. Plus the derivative of y squared is 2y. And again, because we took the derivative of something involving y, we'll multiply this by dy dx. Then minus, well, the 5, well, supposed to be minus 5y. So this is going to be minus 5, because the derivative of minus 5y is just minus 5. And then again, times dy dx. And now the derivative of x squared is minus 2x. And because we did not take any, there were no y's here, we do not have to multiply by dy dx here. And finally, the derivative of -4 is 0 because the derivative constant is 0. So that's step 1. Now step 2 was to collect all of the terms with dy dx on the left side and everything else that doesn't have dy dx, move it to the right side. So here the only term that doesn't have dy dx is that -2x. So we're going to move it to the right side. So I'm just going to bring everything else down. 3y squared times dy dx plus 2y times dy dx minus 5 times dy dx equals, and then just add 2x on both sides. The 2x on the left side are going to cancel, and then on the right side you're going to have plus 2x. So that's step 2. Step 3 was to factor all of the dy dx's out of the left side. So notice that now the left side only has things that involve dy dx. So that means that dy dx is a common factor of all of them, so we could factor it out. So we have dy dx times 3y squared plus 2y minus 5 equals to 2x. So that was step 3, factoring that out. And finally, the fourth step is to divide by the factor of dy dx. The factor of dy dx is the value that you're multiplying it with, which in this case is this whole trinomial. So if you divide both sides by this, we have that dy dx is equal to 2x divided by 3y squared plus 2y minus 5. So the derivative with respect to x of y cubed plus y squared minus 5y minus x squared equals to -4 is equal to 2x divided by 3y squared plus 2y minus 5. Okay? Now, when it comes to taking the derivative implicitly, oftentimes when we take the derivative of implicitly, we are dealing with things that are not themselves functions. So for example, if I were to draw you a picture like this, say something that looks like this, right? It's my x and my y-axis. If you were to look at something like this, this is not a function because it fails the vertical line test. It fails here, here, and here, so it cannot possibly be a function. But we could still take the derivative of it implicitly. We could still do it, and that's because we could take the derivative implicitly. Now, when it comes to finding the derivative of something like this, or an equation that's given implicitly, we have to be aware of what we're working with, because sometimes it makes no sense for us to solve for a problem or take the derivative or try to look for the derivative of a problem for which there's no solution. So if your equation has no solution at a particular point, then it doesn't make sense to find the derivative at that particular point, because you're not going to find it. Okay? But you could actually find the derivative by segments in this graph. So that's actually possible. I'm going to give you an example right now of how we could represent some functions, some equations as functions in terms of y. So representing equations as a function of x. It's y being a function of x. Take, for example, the following function. Let's say you have x squared plus y squared equals to 1. From pre-calculus, you should know that this is a circle centered at the origin with radius 1. This is the so-called unit circle. All right, so if you don't remember from pre-calc, this will be something like this. Where r is the radius and h and k are the center of the circle. So this represents the graph of a circle. Now a circle, again, it's not a function. It fails the vertical line test. It's not one-to-one. But we could actually write this as a function if we limit the domain and we put some restrictions. So what do I mean by this? If we subtracted x's on both sides, so if I subtracted x squared from both sides, then I get y squared equals to 1 minus x squared. And if I take the square root, I get y equals plus or minus 1 minus x squared. Now, this is on the interval x being bigger than 1, the minus 1 and less than 1. If x is 1 or minus 1, then we have 0 inside of this radical. And remember, the tangent line, the derivative is going to give us a tangent line. There is no tangent line here, there's a vertical line. I mean, the tangent line just simply, the slope of the tangent line here is undefined because it's a vertical line. Okay. Now, here from this graph, from this equation, we have two equations that come out. We have y equals the plus square root of 1 minus x squared, and we have y equals minus 1 minus x squared. And graphically, they represent, if you again draw the unit circle, the positive one represents the top half of the unit circle, not drawn to scale. This image is not drawn to scale. So this is y equals 1 minus x squared. And then this next one is the following picture, also from minus 1 to 1. There's minus 1 down here. And this will be the bottom half of the unit circle. This will be y equals minus 1 minus x squared. Now, we were able to rewrite both of this. We were able to rewrite this equation into 2. And now we can actually take the derivative. Now it makes sense to take the derivative, because we know how to take these derivatives. This is y equals, for example, if you were to work with the first one, 1 minus x squared, then you could rewrite this as 1 minus x squared to the power 1 over 2. And then you could see that this is going to be a chain rule problem. with using the general power rule. So y prime here, you could tell that it's going to be 1 over 2 times 1 minus x squared to the power. Remember, you take away 1, so minus 1 half, times, by the chain rule, the derivative of the inside, which is simply minus 2x. The 2's are going to cancel out. So you're left with negative x on the top, and in the bottom, you're left with the square root of 1 minus x squared. So clearly we can now take the derivative with respect to just 2x. We don't have to do it implicitly. So sometimes the whole idea of this problem is that sometimes you are able to actually turn an equation that may not be differentiable into a differentiable function by putting some restrictions on parts of the curve. So since we put these restrictions on the curve, we can now actually take the derivative. Let's do another example. So let's find the slope of a graph implicitly. Right, so let's find the slope of the following. Let's say somebody gives you x squared plus 4y squared equals to 4. Now this looks like the example that we just did, but in truth this is more of an ellipse. That 4y squared actually turns this into an ellipse looking curve. Well, let's see what we have here. First, what we can do, and this is, by the way, at the point, almost forgot, at the point, square root of 2 and minus 1 over square root of 2. All right, so instead of rewriting this, because rewriting this could be a bit annoying, I'm simply going to take the derivative with respect to x implicitly, like we did earlier. The derivative of x squared is just 2x. The derivative of 4y squared is just 8y times dy dx, because we took the derivative of something with respect of a y with respect to x, and the derivative of 4 is 0. Notice that this is much simpler than rewriting this whole thing. You know, if you were to rewrite it, so just put some scrap here. If you were to rewrite this, you have to move that x squared term to the other side and divide both things by 4, and then take the plus and minus square root, and then find whatever restrictions you have to find to actually make it work on the domain. So that's actually much more complicated than taking the derivative implicitly. So now that we have actually taken the derivative, remember step 2 is to move everything that doesn't involve dy dx to the right side. So this is 8y times dy dx equal to minus 2x. We minus 2x on both sides. And now we could divide by 8y on both sides. So we have dy dx equals to minus 2x divided by 8y. And now we could simplify this a little bit more, because minus 2 and 8 share 2 as a common factor. So this is simply minus x in the numerator. And then 2 times 4 is 8, so this is 4y in the denominator. So now we have the derivative. So dy dx is equal to, let me write it here, dy dx is equal to minus x over 4y. Remember that the derivative gives you the slope. So if we want to find the slope at a particular point, then we simply need plug in the point in the derivative and we get the slope at that point. Now the point that we have to find the slope for is square root of 2 and negative 1 square root of 2. So square root of 2 comma negative 1 over square root of 2. So if we were to analyze this at that point, then we have minus square root of 2 on the x divided by 4 times minus 1 over square root of 2. We could simplify this a little bit more. So let's say dy dx is equal to this. And then we could see that this is going to be equal to minus radical 2 over minus 4 over radical 2. This is a complex fraction, so this is going to be minus radical 2. We write it as divided by minus 4 over radical 2. And this is just minus radical 2 times radical 2 over minus 4. But radical 2 times radical 2 is simply 2. So we have minus 2 because of this negative sign over 4. Actually, both of them are negative, so yeah, over 4. And then plus, minus and minus is plus, and then 2 over 4 is the same thing as 1/2. So the slope at radical 2 and minus 1 over radical 2 is 1/2. So slope at radical 2 minus 1 over radical 2 is m equals 1/2. All right.